The properties of the material or medium through which a wave travels determine the speed of the wave. For example, here we show a transverse wave on a string. Pay attention to the 4 colored dots that represent particles that make up the string. As the wave moves to the right, each particle is displaced one after the other from its undisturbed position. In this case, particles 1 and 2 have already been displaced upward, while particles 3 and 4 are not yet affected by the wave. Particle 3 will be the next to move because the section of string immediately to its left, i.e. particle 2, will pull it upward. This leads us to conclude that the speed at which the wave moves to the right depends on how quickly one particle of the string is accelerated upward in response to the net pulling force exerted by its adjacent neighbors. In accord with Newton's second law, a stronger net force results in a greater acceleration, and thus a faster moving wave. The ability of one particle to pull on its neighbor depends on how tightly the string is stretched, that is, on the tension. The greater the tension force, the greater the pulling force the particles exert on each other, and the faster the wave travels, all other things being equal. Along with the tension, a second factor influences the wave speed. According to Newton's second law, the inertia or mass of particle 3 in the drawing also affects how quickly it responds to the upward pull of particle 2. For a given net pulling force, a smaller mass has a greater acceleration than a larger mass. Therefore, all other things being equal, a wave travels faster on a string whose particles have a small mass, or, as it turns out, on a string that has a small mass per unit length. The mass per unit length is called the linear density of the string. It is the mass m of the string divided by its length L. The effects of the tension F and the mass per unit length are evident in the following expression for the speed v of a small amplitude wave on a string. V is the square root of F divided by m divided by L. When we talk about the speed of the wave, we mean the speed at which the disturbance travels through the medium. This does not mean that the individual particles that make up the medium travel with the same speed as the disturbance. For a transverse wave traveling to the right, an individual particle moves up and down, perpendicular to the wave velocity. In fact, the string particle itself undergoes motion characteristic of simple harmonic motion, according to v particle equals a omega sine omega t. The particle speed depends on the amplitude a and the angular frequency omega of the simple harmonic motion, as well as the time t. The speed is greatest when the particle is passing through the undisturbed position of the string, and it is 0 when the particle has its maximum displacement. Thus, the velocity of the wave is constant, whereas the velocity of the particle changes with time. Another important distinction is that the velocity of the wave depends on the properties of the string, and the velocity of the particle depends on the properties of the source creating the wave. In summary, the linear density of a string, or other linear medium, is the mass per unit length. Finally, the speed v of a wave on a string of linear density m divided by L and under tension force F is the square root of F divided by m divided by L.